Hey, good afternoon, everyone. We're going to go ahead and get started. So I'm James Campbell, and thank you all for coming to hear me talk about boats. I like boats, so I'm glad I get to talk about boats. So moving into the talk. So a little bit about me, as you can probably tell by the haircut, I'm in the Coast Guard. So I'm a part of the red team for the US Coast Guard, do standard red teaming things, basically Windows stuff, enterprise networks. But then when I go home and work at night, it typically is on other boat things not related to the Coast Guard. So here I have a couple pictures. So I've 3D printed my own boat to kind of map the Potomac. So that's some fun stuff I do on the side. And then I also get to help with the Maritime Hacking Village in my free time. So we got to go to Tokyo this past winter. I guess we're still in winter, but back in November, got to go to Tokyo, teach a bunch of people about maritime hacking, and the stuff we've done at DEF CON and at that conference kind of inspired me to talk about this on a larger stage. And then finally, I'm a dog dad. That's my dog Pixel. She's great, crackhead though. So, as with most talks for people who work in the government, just the standard disclaimer. This is all of my work. The views, research, and opinions expressed in this presentation are solely mine and do not represent the views of the United States Coast Guard. Another disclaimer added to this is don't do crimes with anything I say. Do it in good faith. So why should people care about maritime cybersecurity? So you might not think about it, but everything we use has probably been on a boat at some point. So 12.3 billion tons of cargo is shipped annually, which equals about 85% of the total commerce in the world. And then even if the thing specifically hasn't been on a boat, parts of the thing probably have. So if you think about ports and the interconnectivity between, you have airports, you have the ports themselves, you have the trains, all of these things are interconnected and dependent on maritime infrastructure. And then if we look at some maritime incidents that have occurred in the past recent history, so we can look at the damage that the Baltimore Bridge collapse caused by a ship going dark for 30 seconds. The ship lost control for 30 seconds and took out a bridge that impacted infrastructure for the state of Maryland and the East Coast for months, and we're still reeling from the effects of this, given the fact that the bridge still hasn't been rebuilt. And then back in 2021, we all remember the cargo ship that kind of tried to go sideways down the Suez Canal. That ended up impacting about 12% of the world's commerce for an entire week until they were able to get it unstuck and back moving. So with each of these attacks, they're just one-off attacks that happen due to mechanical failure or personnel failure. But as we start to look at maritime cyber attacks, the impacts can be coordinated across the globe, causing a much larger impact. So moving into the attack surface of maritime systems, there's a lot. So if you look at the network connectivity, as we're starting to see Starlink installed on commercial vessels and other ships are becoming more and more dependent on internet information. In addition, you have things like ship-to-shore networking for as ships are coming into ports, they're relaying information to port partners before they even get dockside to speed up the transfer of cargo from the ship to land and to those like train terminals and things like that. And then finally, we're also seeing IoT devices like we're seeing in our homes being deployed in these maritime environments. So think about like crane systems utilizing LoRa radios and the bridges themselves utilizing technologies that are based off of these things that just provide a larger attack surface for people to look at. Then moving into like standard systems like AIS. So AIS is a system that allows a vessel to tell other vessels where they're going, who they are, and what speed they're going. So in the grand scheme of things, it's a pretty nice thing to have, but the problem with this and the fact that it's open is that anybody can speak on this. So you can spoof AIS transmissions, which can end up impacting other ships, because when a ship can't see a target, but it's broadcasting AIS, Now they have to go through a procedure to determine if it's a real target or if they're just not seeing it. And then finally, looking at the internal communication protocols. So on chips, you have two main types of non-Ethernet based communication protocols for the maritime electronics. These include NEMA 183 and NEMA 2000. So NEMA 0183 is a serial text-based protocol. If you've ever used like a standard GPS sensor from like a breakout board from like Adafruit or anything like that, the strings that that's dumping out is in NEMA 0183 format. And then NEMA 2000, which is what I'm going to be talking about mainly today, is a CAN bus-based protocol that also has no encryption and no authentication, which we see how well that goes. So then moving into a little bit more about CAN bus specifically before we get into the NEMA parts of things. So what is CAN? So CAN was developed back in the 80s, and the biggest things for this was data error correction and integrity so that way you could have information passed by large electronics or large things emitting EMF, and those transmissions are going to be safe getting past there, and that you're actually able to transmit that data. So think about information going past a generator. With standard communication protocols, they'd be affected by the EMF of that generator, where CAN tries to get past that utilizing its protocol. Some information about CAN specifically is you have this bus arbitration. So when you're dealing with who can speak on the CAN bus at what time, it's done utilizing this arbitration ID. So typically, the lower CAN ID you have, it means the higher priority you have. So if I have a lower priority than other devices trying to speak, they'll shut up as soon as I start trying to talk with that lower CAN ID. And then, as I mentioned, CAN is built for error detection. So you have different checksums, you have frame checks, bit monitoring, acknowledgements, and bit stuffing. So this protocol is meant to be really safe going across these different networks. And for those trying to visualize, we have a CAN network made out of cans at the bottom here. So you all hear CAN, and people who have worked in the car hacking sphere are like, I know what that is. And yes, you do. And it's actually very similar between boats and cars because the boat standard was developed after and on top of the car standard. So for this, some things we can look at in the differences between these is automotive CAN is much faster. So automotive CAN, high CAN, can go at a data rate of about 1 megabit per second. And this type of CAN has been researched extensively since 2010 and well before then as well. So there's a ton of research on the car hacking side and the car hacking scene because it's pretty easy to find someone who has a car who's going to let you plug into it. You might have to ask like 25 friends, but one of them at some point will give in after enough begging. And then when we move on to the maritime side, we see a lot of similarities. It's based off of the same standard, but there's a different message format on top. And you're utilizing a larger identifier to identify the different devices on the network, and you're also speaking at a much, much slower rate. So moving into the NEMA 2000 protocol specifically. So this is where it becomes a little more interesting and a little more boat focused. So this protocol was originally released back in 2001. They were a year late. And the idea of this was to replace the legacy NEMA 0183 networks because those networks had to be manually connected to a main device that was intaking all of that data and correlating it and then sending information out from there. The idea for CAN was that it was modular, so that way I can go buy a sensor from Garmin for my GPS. I can go buy an AirMar sensor for my weather data. I can go buy a different type of depth sensor. And then once I add all this together on the same network, they can all talk to each other. So that sounds great However, as we start thinking about making protocols open for every type of device to speak on, we start seeing how attackers can get into those networks. So with this, the security concerns associated with NEMA 2000 are no authentication. So when you plug a new device into the network, every device is willing to talk to that device like it's a new valid device. There's no encryption, so you can hook straight into the lines and listen to the information that's going across the CAN bus. In addition, with this CAN bus, if you can get any physical access to it, you can plug a number of devices in, because thankfully they've developed a nice, clean, standard screw terminal that you can just screw this adapter into and you can plug right into the network. And again, this was made so that way devices from different manufacturers had a standard way to connect to this NEMA bus. Everything I keep saying just makes it easier and easier for attackers to get access to these networks and these devices. So what's the problem here? Everything you saw with CAN and car networks and car hacking can pretty much be applied directly to boat hacking. The reason you don't know about this is just because it's a lot harder to get access to boats. I know more boat people, like people who have boats, than most of you do probably, and they won't let me plug into their boats. So I'm assuming most people haven't really thought about this problem or even these technologies. So what are some of the attacks we can look at and take from the car hacking world and move into the boat hacking world? So we can first look at spoofing attacks. So instead of trying to mess with any of the devices specifically on the network or trying to listen to the network before we start making changes, you can just start playing data on the bus. Follow the same rules that a device is supposed to follow, and you can speak on the bus just like every other device. You're just your own manufacturer now. So this means you can spoof GPS information, you can manipulate different depth readings, you can forge sensor data, because of course the boat doesn't care that there's a second engine aboard now. And then you can also spoof heading and compass data. So think about how that can be a problem if your ship is utilizing a different compass or heading than is the actual heading. That's how you might get a situation like the Suez Canal ship. Next, you can look at the denial of service. So there's been extensive research on how to do denial of service on CAN networks based on taking up every address that's on the bus. So basically, every device wants to be nice to other devices on the network, especially if that other device has a higher priority. So what we can do is take up all of those different bits that are or we can take up every address that's on the bus with the lowest priority and kick those other devices to new addresses, and keep doing that until we kick all of the devices off and they'll go into their error state. And then finally, if we don't want to cause a big change like adding a new sensor to the network or by creating a complete denial of service, we can look at performing data manipulation attacks or data impersonation. So this involves a little more sneakiness, but it's basically listening to the traffic on the bus before we start speaking. So you can listen for different devices and the messages that they're sending on the bus, listen to that information, copy the header information and other key parts of that message, but modify the different data fields, so that way when you relay that message again, it looks like it's coming from the legitimate device with the correct address, with all of the right information, but now it's just coming from your device, and because you're sending at a faster rate, you don't even have to tell the correct device to stop, because by the time your message refreshes the MFD or the display, it's just going to keep doing that without listening to the original values. So, like I kind of mentioned earlier, getting into maritime cybersecurity is pretty difficult right now. Whether you're coming to a con and hanging out with the Maritime Hacking Village and getting experience that way, or you have a couple other choices like spending upwards of $2,000 to build a home lab, which I don't know about you, but I wouldn't be doing if I didn't know anything about this to begin with. Or you can start trying to scrounge around on eBay looking for cheaper electronics or Pi hats that exist, but even those have an upwards of like $300 start cost. In addition to this, there's some limited resources associated with getting into NEMA hacking and into maritime cybersecurity. So if we first look at the NEMA standard itself, NEMA 2000 is technically a proprietary protocol. And I say technically because there have been a lot of reverse engineering work and projects done to try and reverse engineer some of the protocol. However, if you want the full official protocol, you have to contact NEMA, spend $1,000, then you get to sign the NDA saying you'll never tell anyone about it, and then you can know what the standard actually says, which obviously for us here in the cybersecurity world, we're not too happy with. And then finally, the access problem. I can bet before any of you read this talk, you probably weren't thinking about boat security before this. Even coming now, you're probably trying to think about the last time you were on a boat, if you've ever been on a boat anyways. I've been talking to some people with the village and they're like, I don't even think about boats because I'm from Nebraska. So not a lot of boats there, not a lot of water. So it's kind of a unique problem, but it's a huge problem because even those people in Nebraska are affected by maritime cybersecurity. So at this point you might be asking, so am I gonna go home and just buy a new MFD for $500? Well, that's the point of this talk, and my hope is to lower that bar. And to do that, I created a device called Nemo. Here's a small handheld version. And so Nemo is a platform that's supposed to make it accessible for people to get into maritime security. So the goal with Nemo was to make something portable and affordable that people can make in their own home to get started with this type of technology. The idea for this was the hardware was going to be consumer available and accessible to most people. So you can buy all of the hardware for this board off of Amazon, off of AliExpress, off of name your provider. If they can ship it to you, you can probably buy it. And then with this board, the goal was to provide different capabilities so that way you don't have to go out and spend any money on real products before you start getting working with NEMA 2000. So with this, and on this board, you can send and receive NEMA traffic either internally on the board itself, or you can end up transmitting on a real NEMA network. You can monitor live traffic that's on a valid NEMA network, and you can simulate 12 different sensors on that network and impersonate 11 different sensor or manufacturer IDs. And then finally, I offer an attack mode so you can see what these different maritime attacks look like. So that way we as a community can start looking at ways we can prevent these different attacks. So a little bit more about the board architecture. Here's a zoomed in picture of the board. So for this main chip, we start with a Teensy 4.0. It's an easily available chip. It's now manufactured by SparkFun. So it's a pretty reliable chipset to get now. And the reason we chose this chipset was because it had two CAN interfaces we can get into. And these two CAN interfaces allow us to do two things, transmit and receive, both things we need to do to hack NEMA networks. So on one interface, we're able to send our attacks, we're able to send our NEMA messages, and then on the other interface, we're actually able to receive those same messages, meaning that we don't need other things on the NEMA network to get started with this. And then finally, the key thing here is we provide output to a real NEMA 2000 network, so that way once you get experience working in a lab environment with this, if you do feel dedicated towards doing maritime security research, you can utilize this tool to interface with real NEMA networks. So looking into the specific attack modes, here we're just going into more of the different vulnerabilities, or if you went to the morning keynote, I'd consider these neithers now. But we have device impersonation and denial of service, both of which are utilizing the same NEMA standard, just in a more interesting way. So like I mentioned earlier, the messages are broadcasted to every node. So everything on the bus is receiving all of the same information. There's no validation of that sent data, and and many devices accept the same message type from different devices. So with this, the attack is pretty simple, and I described it a little bit earlier, but we listen for those legitimate messages being sent by other devices. We learn their device ID. We learn other information about the messages that that device is sending. But because we know the message structure based off of that header ID, we can then input our own modified data fields. And then looking at the denial of service, there's limited addresses. Every device must claim an address, and if the bus is full, we go into an error state. So Nemo goes through, it claims every address, and then continues to claim new addresses as those devices try and make new claims, so that way they can act as legitimate devices, kicking them off and putting them into that error state, to where the only recovery method is restarting the actual system. And something interesting about this attack is, if you think about like in a lab network, if I have to restart my device to start speaking on the network again, it's not that big of a deal. I just have to spend the 30 seconds to turn it off and on again. But then as you look at larger vessels like oil tankers or car carriers or anything like that, it's going to be 30 minutes to restart all of the equipment on the ship properly. So that's 30 minutes that the boat might not have its location data. It might not know the depth of the water. You're stopping commerce. Imagine if that were to happen in like a harbor or something like that. So I've done a lot of talking, but I'd like to do a couple demos to show you all what the actual value of this board and how we can actually use this board. And yeah, I'm not doing a live demo with a boat here. I'll just blame it on the snow that I couldn't get a boat in here, but yeah. So moving into, I kind of wanted to go through different stages in these demonstrations. So the first goal was to simulate a sensor in a lab. So here, all I'm showing is that my device, Nemo, can speak on the network and be received by this screen, and that I can modify the data that's going on the bus. So here I'm just going through the attack menu to configure this sensor. And here I'm utilizing this potentiometer to be able to actually change the value of the water depth that the screen is displaying. So if you imagine a ship captain going through and seeing his water depth or the depth of his ship changing, that can have huge impacts, especially as you start to look at larger ships like oil tankers, and now you're worried about groundings. Is this information trusted anymore? So we were able to do that in a lab. So then the next goal is to see if we can impersonate a sensor in a lab. So here we've actually hooked up a depth sensor to the network, and we're reading actual data from that device. And now our goal was to impersonate that device and try and get it to also show up on the screen. So here we can see that attack go. So you can start to see that I'm able to change those values now, despite that valid sensor still being on the network and still trying to transmit. So doing this in a lab is all great, and I'm really thankful that I'm able to have access to a lab that lets me test these types of things, but I really wasn't satisfied with coming here and just being like, I did this in a lab. So the next goal was I was able to find a boat. So I found someone who was going to let me hook into their boat, and would you look right there, there's some nice NEMA connectors that they had just waiting for me. So with this, I was able to get up onto the bridge, and I was able to start playing around with this ship and start to see if my board was actually something I could use on a real ship. Because up to this point, I wasn't sure. I was pretty sure, but this was the only way to be certain that it actually worked. So here I'm going to try and simulate a sensor on a boat. So there is a valid heading sensor on the boat that's providing data here, but instead of just trying to impersonate that data, I'm just trying to speak louder and faster than that device. So here you might see an effect. It might be hard to see. So here I've put the attack into active mode. You can see as I change the potentiometer, some things are changing, and then your heading starts changing. And I don't know about any of you. I've only been on a boat for a couple times on the bridge, but if I started seeing my heading go like this, I don't know what I would do. So here we can see that we're actually able to change that information and able to make these sensors go crazy. I mean, if I saw my heading go from 300 degrees down to 40, I don't know, maybe I'd be in the Suez Canal. So we were able to do that, and we're able to simulate a sensor on the boat. So that's fine and dandy, that's great. But then what about a denial of service attack? So here I'm going to try and run that denial of service on an actual ship to see what that effect would be. And here we just have a screen displaying some of the information off of a gateway that's actually reading live data off of the bus. There's also a couple other artifacts that tell us that something might be going wrong. So you can see that things stop showing on the screen, and then you can hear that there are a couple sensors that start going off as they keep going off. And it was hilarious to me. I didn't realize that this was going to happen at all. But every screen on the bridge started showing error messages. It was the most hilarious thing to me at the time because I had no idea that that was going to be the artifact. But even with this simple denial of service, it's just following what the standard is. We're taking that NEMA 2000 protocol standard and we're abiding by it just in a little more of a malicious way. And we're able to cause all of these sensors to go off, all of the noises to happen, and thinking in the context again of like large maritime ships, the impact that this would have. A captain might not be able to trust his system until an engineer is able to verify that it's valid again. So now we've continued to cause impact to these vessels with just standard simple attacks. And then finally, we have to test impersonating a sensor again, just like we did in a lab. So here, we're going to try and impersonate this depth reading. So like I mentioned earlier, if a ship doesn't know the depth of the water, then you could run into groundings and you can run into other issues that a ship captain might not be willing to accept the risk for. So here, we're actually listening for that valid sensor reading, and then we're replaying it with new data. So I'm just going through the different menu options, and I'm going to assume that the ship doesn't go to 300 feet of water from 5 foot instantly. And we can control that value. And if you think about in an attack sense, here we're showing a dramatic change for a dramatic effect. We're kind of showing that large change is happening. But imagine an attacker on this ship just going and hiding out somewhere on the ship and slowly changing that value over the course of a 3-month journey over the ocean to where you're not really able to validate or cross-reference the actual depth of the water. And then when you pull into port, that depth data is completely different from what you're seeing on the chart. These can have dramatic impacts. And some cynics might say, well, okay, when are you going to get access to the bridge of a ship other than someone letting you on to get access to the NEMA network? And the interesting thing about that is not all NEMA connectors happen to be on the bridge. So this was a NEMA connector, again, nice screw terminal, just the 2 cables screwed together. And this was just outside the bathroom of the ship, just hanging there, that you could just go up and grab. Like I mentioned earlier, NEMA 2000 utilizes those T connectors, which is really handy for me to plug my 3rd connection in. And with the fact that all devices talk on the network, I could have been in this part of the ship, not even near the bridge, causing changes to information that the boat captain's using to navigate the vessel. So with all this, what are the current defenses for NEMA 2000 attacks and CAN-based attacks like this? So the first being physical security. When the protocol was designed, network security was physical security. If no one can access the ship, then we're good. So physical security is still an important part, and the biggest things we can do here are securing these NEMA 2000 lines and ensuring they're only going through places we know and that we have control of. While this isn't perfect, it does handle some of the issues, but as we're starting to see more internet devices become connected into the NEMA network as well, so that way we can play our Bluetooth music on a device that's getting power from the NEMA network, we're starting to see that physical security is not something we can rely on as heavily. And then finally, if anybody else has experience with, again, the car hacking scene or CAN hacking in general, there technically are companies that claim to have intrusion detection devices, and I'm not going to speak on the specific validity of these devices. However, they do happen to be expensive. They're limited in their adoption, so they're being implemented by small yachts, but not large commercial vessels. And at the end of the day, they're only detection mechanisms. So even if your device is on the network, sending malicious data, and this device is going off with its really annoying beep noise, you still have to find where that device is. And that's eating time out of the crew and the ability to trust the data on the bridge again. So there's not really any great defenses for these types of attacks yet, but that's what we're trying to hope and build out. So then what's next? So leaning kind of more onto my red team mindset of EDR evasion and getting past IDS platforms, it's the standard process. You first analyze what the detection mechanisms are. You then brainstorm and develop the different techniques to bypass it. You then test that effectiveness, and if it works, if your bypass works, then you think about how could this be detected. And then you go through that cycle a multitude of times to try and develop a better IDS solution. And that might include getting away from listening to the NEMA sentences and that NEMA data and looking more at the electrical components of NEMA 2000 and the specific electronic characteristics of these devices. And then finally, NEMA, this great organization, has made us an Ethernet standard. Again, with this standard and with boating standards, these things get released and then they don't get implemented for 20, 25, 30 years. So NEMA 2000 came out in 2001. It's still not deployed to a ton of vessels. It's deployed to most, and the new vessels are getting NEMA 2000. However, vessels built out in the 80s are still based on that NEMA 0183 standard. So NEMA 1net came out back in about 2010, 2013 timeframe. People still on like Reddit and maritime forums and stuff are like, is this thing real? And the standard's been out for 13 years. So it's going to take a while for this standard to get implemented. And there's still issues with this because this standard still relies on information being provided by NEMA 0183 networks and NEMA 2000 networks. So we're still seeing that even though we have a new standard that's supposed to be more secure, this standard is built with the idea that we're going to continue relying on these NEMA 2000 networks, which are susceptible to the attacks that NEMO can do and the different device spoofing that NEMO can do. So finally, just wanted to give a special thanks to some friends who put in a lot of effort to help me over the past couple months in getting this product up, testing it, providing ideas. So special thanks to Joram, Caitlin, and Dean. And then I want to give a special shout out to the Maritime Hacking Village. If no one knows about them, they were here yesterday, but they're here to bring maritime security to people, to give people the ability to access that $1,000, $10,000 equipment without actually having to purchase it. So highly recommend you all reach out to them. And then finally, here's a link to the NEMO project. So all of the code for this board, the specific schematics, all of the information of how it works, how you can use it, how you can build it, are all open sourced on GitHub for people to get into this and get actually excited. And if anybody is actually going to build it and go through, I have about 10 PCBs already printed, if anybody wants one, to go build one of these at home. So thank you all for coming, and if there's any questions, I'm happy to take any. Yep. Oh.
So you mentioned the nautical standard was created, nautical CAN standard was created after the automotive one, but it was slower. Was there a particular reason for that, like electrical or anything?
I don't know if there was a specific reason why they made it slower, primarily to make it just more reliable, I'd presume. But I don't know any specific reason why they slowed it down by a quarter of the top speed.
And then regarding the newer Ethernet standard, so if someone was looking at, say a cruise ship that was built today, would that be using the 2000 standard or the new Ethernet-based standard?
My understanding is that, I only heard about the NEMA 1 standard since researching this, and I haven't heard anybody else really speak about it. So my understanding is that they'd be reliant mainly on that NEMA 2000 standard because those sensors are so common and so reliable now because they're trued and tested. I will say as we start to get to bigger and bigger ships, they'll utilize different types of systems across. So they'll be reliant specifically on like NEMA 2000 for like sending bridge data back and forth, but like the electrical data for the generators might be running like Goose or something like that, like a different type of protocol.
Thank you.
Yep.
Hey, thank you, that was really cool.
Yeah.
I think you definitely showed like if you can physically get on the boat, you can own the boat, it sounds like. And you mentioned it at one point, but I am really curious if you have any examples of like, network connected, like RF connected hardware that is typically on that NEMA network that someone who's like on the shore, has internet access, has radio access, could somehow get into.
I'm glad you asked. So kind of going back to the AIS I mentioned earlier being an attack surface. So if we think about AIS being broadcasted and trusted by all of these ships, those AIS sentences are actually also being broadcasted on the NEMA network itself. So I haven't seen any specific attacks of like sending a malicious AIS message on the bus, but what this kind of enables is the ability to implant a device on the ship at some point, which is sadly a lot easier than you might think with some social engineering and a bright yellow vest. If you can get something implanted onto the bus at some point, then what that would allow is the ability to send out like an AIS message for command and control. And then doing that, you could execute an attack while the ship is underway as opposed to just causing impact while you're on the ship directly. Any other questions? Yeah.
I'm interested in when you get larger ships, they have NEMA networks, but some of them also have more like OT, ICS components for power plants or other industrial equipment going on. Do those types of networks ever interact with the NEMA network? I'm thinking the line of thought of the NEMA network potentially being an entry point to something even more dangerous than just playing with sensors.
So typically we don't see the NEMA network connected to like the electrical grids or those systems specifically. But what we do see is the NEMA information being broadcasted up to a like HMI or data collection system, because these ships want to collect this data to have logs later to look at for diagnostics, things like that. And then we're seeing that like those systems are the systems that are running like Windows 7 or stuff like that. So it's that balance between if you get onto the IT network, you kind of have access to all of these different other ICS environments on the ship.
So when you were talking about the spoofing before, the relative benefit of just spamming out a bunch of new traffic versus copying and impersonating an existing sensor, is the main reason why you'd want to impersonate the existing sensor specifically for that like UI interface that they have up on the bridge, and if you don't do that, just spamming some random thing won't show up in the interface and won't achieve your goal?
Yeah, so the benefit of an impersonation attack as opposed to just spoofing a brand new sensor is if these devices like that IDS system are set to listen for specific devices and allow devices on the network, by impersonating, you're not bringing anything new on that display or making that device realize that something new is connected. It just thinks that you're the valid device talking. It doesn't really pay attention to like the speed at which the messages are being sent, because on the bridge, it's only refreshed at like 1 hertz, because that's as fast as the sensor should be sending data. So there's no like fluctuation even really. Yes?
So I recently went through a pretty deep dive security analysis of AirInc 429, which is the avionics equivalent of a lot of this, at least as far as I can tell. Obviously, airplanes don't have a lot of room to hide in a bathroom and plug into stuff, but a lot of the way that works is the fact that the bus is unidirectional. Is this the same, or is there any bidirectional capabilities to something with NEMA?
What do you mean bidirectional versus unidirectional?
I'm not entirely sure. I'm just curious and asking questions.
Okay. If your question is like, can anything talk to anything else on the bus?
Yeah.
Yes.
Okay.
So NEMA is made for that. NEMA is made so that way any device on the network can talk to other devices. That way, like even if you set a specific destination device, so if in your NEMA message there's a destination field, even if you set that to a specific address, every device receives that information anyways. So it's a broadcast-based protocol. Any other questions? Cool.
Actually, I have a question.
Yes.
So does Nemo, your tool, or have you yourself explored fingerprinting devices on a NEMA bus or on a CAN bus, what they might do?
So I haven't. I actually have to look into that. I bought that IDS system this week to look at during the snowstorm. But so the problem with fingerprinting NEMA devices is if you're looking at the protocol level, it's spoofable. So you run into the issues of that. There is some research being done into the actual fingerprinting the electrical characteristics, but there's been nothing like super public or like a ton of research on that yet. It's still like in very early development because most people haven't really thought about boat security to this point.
Cool. Thank you.
Yeah.
Anyone else? Oh, we got one.
Are there any competing standards, or is it kind of like any boat across the world is probably going to be running NEMA?
From my understanding and what I've seen, everything would be running NEMA. NEMA is like the standard that everybody would use for boat communication. You might have some boats that try and go mainly towards the NEMA 0183 protocol because the system they use is reliant on that serial-based communication. But usually it's one of those two that I've seen.
Cool, thank you.
Yep.
I'm just curious, even for large ships, is it really just one bus network for the whole ship, or do they split it up into a tree or something like that? Or
So
if you happen to know.
you can only, to reliably ensure communication across the bus, NEMA recommends only connecting about 50 devices at most. And typically off of those bus trees I had, that backbone, you're only supposed to have drops up to 6 meters based off of the standard. So some of them will have different buses throughout the network, but then what you'll see is a single terminal or a single network is relaying NEMA traffic over the network so that way it can be piped into the other buses so that way they can communicate. And that's what the NEMA 1 net is trying to get into and trying to secure. Awesome. Anything else? Sick.
Awesome. Can we get another round of applause for James and this sick, really interesting, really different talk?